So as I mentioned at the end of our last class meeting, I'm just going to use today to go over some more example problems to illustrate transient analysis techniques. And then after I work a problem or two, I'm going to open the floor up to any questions you may have with regards to a review, and we'll be off to the races. All right, so the first circuit that I would like to look at today will be this one, in which we have a 10 kilo ohm resistor up here on top, and then this middle branch, which contains a 5 kilo ohm resistor and a 20 kilo ohm resistor. Here we're going to have a switch that will close at t is equal to 0, and this is connected to a 40 volt source we have a capacitor here having a value of 100 microfarads, and we're going to put a 100 volt source over here on the right hand side. The quantity that we are going to be interested in for this particular circuit, excuse me, let's scroll down here, will be the current flowing through our 10 kilo ohm resistor. Let's define that current to be in this direction, and we'll call it I of t. And because this circuit contains a capacitor, we're going to also have to pay attention to our capacitor voltage, Vc of t. So this circuit, I believe, will obviously be a total response problem because we are switching in the 40 volt source as opposed to taking it out, and the 100 volt source is always going to be connected to the network that contains the capacitor. So from that, we are going to have to analyze our circuit at t is equal to 0 minus, t is equal to 0 plus, and t is equal to infinity. So our first step, as always, will be to analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, our circuit is at DC steady state, which means our capacitor is going to be replaced by an open circuit. Additionally, our switch will be open. So what our circuit is going to look like is something like this. And let me identify our quantities of interest. So we're going to have our capacitor voltage VC at 0 minus. And we're also going to have our current I of t directed to the right, like so. So, does anybody have any thoughts or ideas about how we can determine either of our quantities of interest? Sorry, I'm having trouble scrolling down here. I believe Devarier just said mesh. Give me just a moment to sort out. All right, so let's work with what I believe I saw Devarier saying we should try mesh analysis. So if we employ mesh analysis, here, we'll have this mesh current, which we can call IA, and that's actually it. There are no other mesh currents because down here at the bottom, we have an open circuit from our capacitor in the middle, and we also have an open circuit on the left from our switch being open. So if we applied mesh around this particular loop, we would just have 10 kilo ohms times IA plus 20 kilo ohms times IA plus 5 kilo ohms times IA is equal to 0, which implies that IA has to be 0. So let me write that down. So KVL around mesh A, starting from the bottom left-hand corner, we would have 10 kilo ohms times IA plus 20 kilo ohms times IA plus 5 kilo ohms times IA is equal to 0, which means IA must be 0 amps. And from this, we can say that I at 0 minus, which is the same thing as our mesh current IA, is also 0 amps. Does anybody have a problem with that analysis? All righty. So how can we determine VC at 0 minus then? All right, since nobody is suggesting anything, I am going to make a suggestion. I am going to suggest that we write a Kirchhoff's voltage law equation around this loop. Now, this KVL equation will involve us taking the voltage drop over the 20 kilo ohm resistor. I'm going to express the voltage in this direction. And by inspection here, really Ohm's law, I can observe that the voltage drop over the 20 kilo ohm resistor has to be 0 volts because we determined that our mesh current IA was 0, and 0 times 20 kilo ohms is 0 volts. So performing KVL around our bottom right hand path yields negative 100 volts plus 0 volts plus VC at 0 minus is equal to 0. And from this, we can see that VC at 0 minus is 100 volts. There's a large possibility that many of you determined it was 100 volts without doing this formal Kirchhoff's voltage law and all that kind of good stuff. And if you did, that's wonderful. But I wanted to more explicitly prove that it was 100 volts than just saying it and having you guys just agree with me blanketly. All right, so how do we feel about our analysis here at t is equal to 0 minus? Anything wild or crazy that didn't make sense? Not too crazy yet. Thank you, Sarah. All right, so let's move along to step number 2. This will be to analyze our circuit at t is equal to 0 plus. At t is equal to 0 plus, our switch is closed, which means the 40 volt source is now connected to the rest of the circuit, and our circuit is no longer at DC steady state. So we're going to have to replace our open circuit with something. Okay, so let's draw what we've got here. So here is our 10 kilo ohm resistor. Our 5 kilo ohm resistor, and our 20 kilo ohm resistor. On the left-hand bottom, we're going to have our 40 volt source because our switch now looks like a short circuit. On the right-hand side, we have our 100 volt source, like so. And in the middle, we are going to replace our capacitor with a voltage source that has the same polarity as VC at 0 minus, as well as the same value. So this represents our capacitor voltage at t is equal to 0 plus, and we know that VC at 0 plus must equal VC at 0 minus, which was 100 volts. And our goal now is to determine this current I at 0 plus. Does anybody have any suggestions? So Devarier has suggested mesh analysis. And while there's nothing wrong with that suggestion, in fact, let's do mesh analysis, and then I'd like to show you what I believe to be an easier route. Okay? So here's our mesh current IA. Here's our mesh current IB. Here's our mesh current IC. We don't have any dependent sources, so we don't have a controlling variable relationship to write. We don't have any current sources, so we don't have any current relationships to write. So we can just go ahead and get working on our Kirchhoff's voltage law loops. Okay. So KVL at mesh A gives us 10 kilo ohms times IA plus 20 kilo ohms times IA minus IB plus 5 kilo ohms times IA minus IC. We'll set this equal to 0. Thank you, Sarah. You are correct. I got my I got my B and C mixed up. So it should be C here and B here. Thank you for noticing that. Next, I'm going to do KVL around mesh B. So I'm going to have to jump back and forth between the pages here. So if I'm not mistaken, the first thing we would see would be the negative polarity terminal of the 40 volt source. Then we see our 5 kilo ohm resistor. We're going to have IB minus IA. And then we're going to see the positive polarity terminal of our 100 volt source that is replacing our capacitor. And we set this equal to 0. And I'm just going to go back real quick and make sure I didn't mess anything up there. So negative 40 plus 5 kilo ohms times IB minus IA plus 100 volts. Okay. So that seems all right. Now we'll do KCL at mesh C. So we would see the negative polarity terminal of the 100 volt source that's replacing our capacitor. Then we see our 20 kilo ohm resistor. We're going to have a current of IC minus IA here. Then we see the positive polarity terminal of our 100 volt source on the right hand side. And set this equal to 0. Let me just double check here. So negative 100 volts plus 20 kilo ohms times IC minus IA plus 100 volts. All right. And so now I'm going to need to solve this system of 3 equations, 3 unknowns simultaneously. So I'm getting my equation solver ready here. So in my first equation, my coefficient for IA is 10 plus 20 plus 5 kilo ohms. So that looks like 35,000 to me. My coefficient for IB is negative 5,000. And my coefficient for IC is negative 20,000. And my constant term is 0. In my second equation, my coefficient for IA is negative 5,000. My coefficient for IB is positive 5,000. My coefficient for IC is 0. And then I'm going to have 40 volts minus 100 volts when I move those constant terms to the right-hand side. So 40 minus 100, I believe, is negative 60. For my third equation, my coefficient for IA is negative 20,000. My coefficient for IB is 0. My coefficient for IC is positive 20,000. And then my constant term is going to be 0 because I'm going to have 100 minus 100. And when I solve this system, I find IA is negative 3 over 500 amps, which is the same as negative 6 milliamps, I believe. I get IB to be negative 9 over 500 amps, which is negative 18 milliamps. And I get IC to be negative 3 over 500 amps, which is once again negative 6 milliamps. Okay. So I 0 plus is the same as IA, which is negative 6 milliamps, according to our mesh analysis. Okay. Now I'd like to show you a slightly different way to do this, and I believe it to be significantly easier. Okay. What I'm going to do is I'm going to write a Kirchhoff's voltage law equation around the perimeter. I'm doing this because the only unknown voltage drop around the perimeter is the voltage drop over the 10 kilo ohm resistor. And the voltage drop over the 10 kilo ohm resistor is just 10 kilo ohms times the current I'm trying to find. So if I write that KVL equation, KVL at perimeter, I may have misspelled perimeter, but I don't think that'll matter. We would have negative 40 volts plus 10 kilo ohms times I 0 plus 100 volts is equal to 0, which implies that I 0 plus is 40 volts minus 100 volts over 10 kilo ohm, or negative 60 volts over 10 kilo ohms, which is negative 6 milliamps. So we got the exact same relationship, or the exact same value for I at 0 plus, but we had to do a lot less work. So this is why I suggest that you guys not default to just using nodal analysis and mesh analysis and things like that. Run through if you could use KCL, KVL, or Ohm's law first to get an easy relationship like the one I've illustrated here before you go use nodal and mesh. Because while nodal and mesh are very powerful tools, they take a lot of time to use because you have to make sure that you set up the system of equations correctly. Whereas the single KVL equation around the outside loop here got us the same result with a lot less effort. Okay, so there's nothing wrong with doing mesh here. We got the correct answer, but it's a more cumbersome method than was needed to get the result we were looking for. All right, so how did you all feel about our analysis here at t is equal to 0 plus? Anything confusing or need addressing? All right, let's move along to t is equal to infinity. So at t is equal to infinity, our switch is closed and our circuit is at DC steady state. So that means we are going to have a circuit that looks something like this. Here is our 10 kilo ohm resistor. Here is our 5 kilo ohm resistor. Our 20 kilo ohm resistor. Our 40 volt source goes here. Our 100 volt source goes here. Our capacitor looks like an open circuit. So here is I at infinity. And although we don't particularly need it for anything, let's go ahead and solve for VC at infinity as well. So, any thoughts on solving for I at infinity or VC at infinity? Absolutely. So effectively, based on our prior results, we know right off the bat that I at infinity is going to be -6 milliamps, because if we performed KVL around the perimeter like we just did in the last analyzing our circuit at t is equal to 0 plus, we have the exact same loop. So that didn't change at all. So 100%, that is a very reasonable thing to do. How might we go about solving for our voltage VC at infinity? All right, since nobody is suggesting anything, the bottom right loop. Okay, so the reason why we can't just use the bottom right loop. So let me be clear here. I believe this is the loop that Sarah is suggesting. We don't know what current flows through the 20 kilo ohm resistor right now. That being said, if we amend this very slightly, if we write a KVL equation around this loop, we could figure out how much current flows through the 5 kilo ohm resistor and the 20 kilo ohm resistor. Because we know that there's no current that can branch off. So effectively, all of the current that flows through the 5 kilo ohm resistor also has to flow through the 20 kilo ohm resistor. And then from there, we could use either the bottom left-hand loop or the bottom right-hand loop once we know the value of that current to find VC at infinity. Okay. So our bottom path is going to wind up giving us, let's call this current, just for lack of a better term, IB. So around our bottom path here, we're going to have negative 40 volts plus 25 kilo ohms times IB plus 100 volts is equal to 0. From this, IB is 40 volts minus 100 volts over 25 kilo ohms. I don't want to make a mistake doing mental math here, so I'm going to put this in my calculator. So negative 60 divided by 25,000 comes out to be negative 2.4 milliamps. Now, using Sarah's suggestion, I'm going to write a KVL loop here. Bottom right-hand path. And I'm going to have negative VC at infinity will be equal to, sorry, getting ahead of myself, negative VC at infinity plus 20 kilo ohms times IB plus 100 volts is equal to 0, sorry. And therefore, VC at infinity is 20 kilo ohms times negative, 20 kilo ohms times 2.4 milliamps. .48 volts. Let me make sure I'm doing my algebra correctly here. So when I move VC at infinity over, .52 volts. All right, so does anybody have any questions about the analysis that we did here at t is equal to infinity? Shouldn't it be positive? Please clarify what it is. All right, so I don't believe so, but this may be an algebraic mistake on my part. So let's look at it. Okay. So what I've done here is I have moved this VC at infinity over to the right hand side. Okay. All right. So it seems like it's resolved. No, not a problem at all. By all means, if something seems fishy, ask about it, because Lord knows I make mistakes all the time. You guys have witnessed plenty of them. So if it seems like it doesn't make sense, ask. There is a very good probability that I've made a mistake. So I'm not in any way, shape, or form offended by you saying, hey, maybe you did this wrong. I know I might have done it wrong. All right. So any other questions regarding our analysis at t is equal to infinity? All right, nobody's saying much of anything. So let's move along to step number 4. Or excuse me. Sorry, I can't count. This should have been step number 3. And now we're on step number 4. Goodness gracious, can't even count today. Which will be to determine our time constant tau during the transient condition. Okay. So that is going to involve finding CEQ, which, since there's only one capacitor in the circuit, I feel like that's pretty straightforward. This should be 100 microfarads, if that is the correct value of the capacitor from the problem statement. It looks like I have remembered it correctly. Then we're going to have to find REQ. To find REQ, we are going to find the Thevenin equivalent resistance seen by the capacitor, and we need to be looking at a dead network during the transient condition. So that means we're going to have all 3 of our resistors. So here's our 10 kilo ohm resistor. Here's our 5 kilo ohm resistor. Here's our 20 kilo ohm resistor. Trickier than what we've done previously. So I'm going to go back to our old My apologies. It seems like my laptop disconnected from the internet. Just waiting for the screen to come back up. There we go. All right. So as I was trying to say a moment ago, I'm going to rely on our old school resistor combination methods here, just because this is maybe a little more difficult than the things we've done in the past. So this is node A. My apologies again. Apparently the Wi-Fi here in Neskin Hall is not working particularly well. I don't understand why. It is what it is. Seem to have caught up maybe. So as I was again, I apologize for the spotty internet connection here on campus today. I do not know what's happening. So our equivalent resistance is 5 kiloohms parallel with 20 kiloohms, which I believe comes out to be 4 kiloohms if my mental math is correct. 5 times 20 is 100. Divided by 5 plus 20, so 100 over 25 seems like 4 to me. From here, our time constant tau is 4 kiloohms times 100 microfarads. So I'm going to throw this in my calculator just to make sure I don't get the units wrong. So 2/5 of a second. And from that, 1 over tau is obviously 5 halves per second. From here, we move on to step number 5. Which is plugging things in to our generic equation. Let me scroll up here, Sydney, and I will explain it to you. So the 10 kiloohm resistor is connected on both sides at node B. Effectively, the 10 kiloohm resistor is in parallel with the short circuit at the bottom, and so it doesn't contribute. So if we drew this out old school way, like we did at the very beginning of class, here's terminal A, here's terminal B. Between A and B, we have our 5 kiloohm resistor. Between A and B, we also have our 20 kiloohm resistor. But our 10 kiloohm resistor is connected between B and B. So it's shorted out and does not contribute. No problem. I'm just glad the internet hasn't dropped me so that I was able to explain it. All right, so our generic equation is y of t is equal to y at 0 minus or t less than 0 minus and it is y at 0 plus minus y at infinity, e to the negative t over tau plus y at infinity, or t is greater than or equal to 0 plus. So our current I of t will then be, I believe it was 0 at 0 minus, and then it's going to be negative 6 milliamps minus negative 6 milliamps, which, if I'm not mistaken, comes out to be 0, e to the negative 5 halves t minus 6 milliamps, where t is greater than or equal to 0 plus. So effectively, it's a constant value of negative 6 milliamps. Our capacitor voltage is going to be 100 volts, E less than 0 minus. And then it is going to be 100 volts minus 52 volts. Let me just double check that value here. It's been a minute. Yes. E to the minus 5 halves t plus 52 volts, t greater than or equal to 0 plus, which we could simply call this 48 volts. All right, so we've spent about 45-ish minutes, including times that I've been dropped from the internet, on this one particular problem. Do we want to work another transient analysis problem, or would we like to talk about the exam now? So let me answer Sarah's question first. Is the exam still offered at 8 different times? Yes, that is correct. The exam is still offered at 8 different times. There will be a Thursday afternoon and Thursday night, Friday afternoon, Friday night, Saturday afternoon, Saturday night, and Sunday afternoon, Sunday night version of the test. To answer Devarier's question, would we ever see a transient problem with a dependent source on the test? I have done that in the past, but I do not believe I will be doing that for you guys for this particular exam. I didn't work out any problems with that, but how you would approach that would simply be using a test source method to find the equivalent resistance of the network containing the dependent source, and then other than that, it's exactly the same as what we've done here. Okay, so I don't intend on giving you a problem like that, but you would treat it using the methods that we are going to be going over for this exam anyway. So just using a test source method to find the Thevenin equivalent resistance, and then from there, you know tau and can plug stuff in. Any other questions? All right, so I'm just going to talk for a couple of minutes about what you should expect to see on the exam. Okay. So the first thing will be Norton equivalent circuit. Without dependent sources. This will be 2 to 3 problems. Then Thevenin and Norton equivalent circuit with dependent sources. Also 2 to 3 problems. There will very likely be a circuit which only contains independent sources or an independent source, and I'll ask you to calculate the Thevenin equivalent resistance directly using the test source method. And then there may be another circuit where I ask you to find either the Thevenin voltage, the Norton current, or both. Okay, so it just really depends on how I'm feeling. But yeah, you should expect to see, one circuit to analyze that doesn't contain dependent sources, and then up to 2 circuits to analyze that do contain dependent sources. And you're expected to know how to find the Thevenin and Norton equivalents of all of that. Then we get into our capacitor and inductor material. So inductors, let's call this 2 problems, and the equations that you will need to know to handle these inductor problems are: the voltage drop across an inductor is equal to L DIL by dt. The current flowing through an inductor is 1 over L times the integral from T naught to T of VL prime dt prime plus IL at T naught. Power absorbed by an inductor is VL times IL, our generic power relationship. Also expect you to be able to apply L times IL times DIL by dt. And then the energy absorbed by an inductor, which is 1/2 L IL squared. You are not going to be given an equation sheet. You are not allowed to use an equation sheet. So I'm expecting you to, I hesitate to say learn, memorize these 4 equations. Okay. Then there will be a couple of capacitor problems. And I expect you to know all of our capacitor relationships as well. So those are IC of t is equal to C dV by dt. dC of t is equal to 1 over C times the integral from t naught to t of IC t prime dt prime plus VC at t naught. PC of t is VC times IC or C VC EVC by dt. And the energy stored by a capacitor, 1/2 C VC squared. Then we'll have a DC circuit with inductor and capacitor. So I'm expecting you effectively to calculate inductor current and capacitor voltage and tell me the energy stored in the energy storage elements. This is going to be one circuit, 1 to 2 problems on this circuit. Then there's going to be, I'm going to call it an AC. What I mean by that is that the voltage or current depends on time with an inductor or capacitor. And this will be 1 to 2 problems. I'm going to put an aside here. Homework 12.3 and homework 12.5. So that's the style of problem you should expect to see. It's not going to be exactly that problem, but something very similar. I believe we talked about this over a week ago, where I told you very specifically, I like those problems and I like to put things like that on the exam. So I'm just giving you fair warning again. You should absolutely work those two out before you take your test, because you're going to see something very similar. Let's see. Then we're going to have a natural response transient problem. I don't know if it'll be an LC circuit, or excuse me, not an LC, an RL circuit or an RC circuit. You will know that it's the natural response problem because I am not going to ask you what's going on at t is equal to infinity. Okay. And this will be, I think, 4 questions. And then there is going to be a total response problem. You'll know it's the total response problem because I am asking you what's going on at t is equal to infinity. Okay, so you don't need to be able to know the difference. When I ask you to analyze the circuit at t is equal to infinity, know that I'm expecting you to include that information in your generic equation. If you get a RC circuit for the natural response problem, you'll get an RL circuit for the total response problem, and vice versa. So you'll have one RL circuit to deal with, one RC circuit to deal with, but you won't know which one is the natural response or which one is a total response. It's going to switch between the exams. And let's call this 4 to 5 questions. Okay. So that's all the material that'll be on your test. It's really only 3 large topics: Thevenin and Norton equivalent circuits, capacitors and inductors, and then transient analysis. Anybody have any questions about any of this stuff? All right, since nobody has any, is it safe to assume the practice tests are similar? Yes, Sarah, absolutely. I believe the practice exams that I have uploaded might be older tests, so they have 35 questions as opposed to 25 questions. But it's covering the exact same material, there'll just be fewer questions. Yeah, if you're looking for things to study, the practice tests are a great thing to look at, as well as the in-class assignments. So that would be in-class assignment number, I want to say 9 through 15. Any other questions? All righty. Well, I will lurk on Zoom if anybody decides they have anything they'd like to ask. Otherwise, I hope you guys have a great rest of your afternoon. Study, practice, all that kind of good stuff. And if you have any questions after the Zoom is over, feel free to email me about, questions from the practice test or anything like that. And I will be available if people actually show up on Thursday during class time to answer questions as well. But if you don't bring questions with you on Thursday, I'm not going to do anything.